time along any path from start to finish. You understand what I'm saying? If you're on this trajectory at this point, at that point, the particle has a position and a velocity, right? Position is the x, the velocity is the slope. Then you can form the Lagrangian there and multiply the Lagrangian by a small interval dt. Then you integrate it over the whole path. That's called the action. So the action is the integral of the Lagrangian from start to finish. So for every path, you can compute an action. If you say, what is special about the classical path? Is that the classical path is a path of least action. That's the way to distinguish the actual path. It is privileged in the following sense. It has less action than any other path, but action is defined as the integral of Lagrangian. So any questions about this thing? What's called the principle of least action. That is the new postulate of mechanics.
I have one.
Yes.
Sir, in the least action that we studied in classical mechanics, it says that our action should be like our this integral should be minimum, right? But in the Fermat principle, when we study action, it say extremum. So,
That is correct.
so,
Yes.
so there is something like in that we say extremum, in this we say minima.
It is called the least action, but technically you're right. It is not the path of least action. It's the path of stationary action. In other words, if you have a function of x, a minimum and a maximum are both points where the function is stationary, but only the minimum is where the function is the minimum. So you don't really need to know if the action is a maximum or a minimum. You need to know that it's a stationary point.
But suppose we get two paths for which our functional is for one our function is minimum and for one it is extremum for maximum. So what path system will choose, minimum or maximum, if we have two extremum? One is minimum and one is maximum. Then which path?
Well, usually it's the minimum. But I don't think, in fact, very often, suppose you say, which one should I choose? Which one is the right one? You know what you do in the end? You find out the trajectory and compare it to what Newton says. And you'll always find it's the path of minimum action. So we have to keep going back to Newtonian mechanics to make sure this is the right answer. In fact, how do we know this Lagrangian equation that comes from minimizing the action? Correct answer, only because it agrees with Newton. So in the end, the real test is with Newton. So usually, we never go beyond requiring that it's a stationary point.
Okay, sir. Thank you. But sometimes we also get maxima in perhaps if there's a problem in optics where we have two sources in the foci and the light will go to the path which is maximum. So there we got maxima, not minima.
I see.
Yeah,
okay.
Sir.
Yes. I think the important thing is that it should be stationary. That's all we can say.
Okay, sir. Okay.
If you get two solutions, I've not seen many problems in mechanics where you get two solutions. But if you get two, there's no way to choose between them using the principle of least action. You have to compare it to some other way, like Newton. Also, Mr. Lagrange doesn't tell you what the Lagrangian should be. He just says, if there is some function of x and x dot, which when you put it in the formula, will give you the equation of motion, that the function should be t minus b, is something we cook up so that it agrees with Newton. There are problems where the Lagrangian is not t minus b. For example, if you have a magnetic field, it is not t minus b. So the answer is Lagrangian is whatever you got to put into the machine so that the equation you get out is the right equation. And how do you know it's the right equation? You know because it obeys Newton's laws. So Newtonian mechanics is not completely banished from the picture, but there are many advantages of using the Lagrangian picture. Anyway, if this is the action, the principle of least action says, if you go to the classical path, it's the path of stationary action, and you can use that to determine the path. And I will tell you roughly what happens. So here's the picture you have. It's a very schematic picture. It says, on the x-axis, I'm calling the path. Of course, the path is not a single number. Path is a whole trajectory. But imagine that you can somehow number all the paths from left to right, and you move in the world of all possible paths, and you plot the action for each path, at the stationary point, here, S does not change the first order in the deviation. For example, if you're a function of one variable at the stationary point at the minimum, df dx is 0. Another way to say this, at the minimum, if you change x by an amount delta x, the change in the function is delta x squared. Normally, if you're at some point here, if you change the function by delta x, the function will change linearly in delta x, and the coefficient will be the slope. But at the minimum, there's no change proportional to delta x. That's what you also mean in the path integral formalism. I mean, in the Lagrangian formalism, if you take the classical path and you deform it a little bit, then you compute the change in the action proportional to the first order in the deformation, and you set it equal to 0, you get the Euler-Lagrange equation. Now, I don't want to do that now. This is not a course in mechanics, so I'm going to just stop there and tell you this is how you get the Lagrangian equation of motion. The main point for us is that at the stationary point, which could be maximum or a minimum, the function does not change when you change the argument. The function here is the action, and the argument is not a number, but an entire trajectory. And you change the trajectory x classical by an amount x classical plus delta x, then you will find the change in the action that's got a term proportional to delta x and delta x squared. Set the part proportional to delta x to 0, you will get the Euler-Lagrange equations. Okay, now I'm going to do quantum mechanics, so it's a good time to ask any other questions. In fact, when we see why this works, you will see what Keshav was saying. Sometimes even a maximum can be as good as a minimum, and you will see why they're equally good. It's a matter of luck which one nature will choose. So in quantum mechanics, I'm just going to do a lightning fast summary of quantum mechanics. And it goes like this. The state of the system, which used to be given by two numbers, x and p, is now given by a function of x called the wave function. The wave function is some function of x plotted across the real axis, and it need not be a real function. So what I've shown is a real function. It doesn't have to be real. And we all know that the role of the wave function is that its absolute square is the probability density of finding the particle at x. Namely, px delta x is the likelihood of finding it between x and x and delta x. Now, you cannot say where does it come from. This is the new law. You don't derive it. And the second thing you need to know, if you know the state, you also have to find out how the state changes with time. So in Newtonian mechanics, the state is either x and p or x and x dot, and it changes according to either Hamilton's equations or Newton's laws or Euler-Lagrange equations. They're all the same. In quantum mechanics, the rate of change of the state is given by IH part d psi dt is h psi. In the x representation, h psi looks like this. Now, I'm going to use one other feature. I don't know how familiar you are. The function psi of x is really representative of what's called a ket. The ket represents the vector without choosing a basis. It's like an arrow in 3 dimensions pointing somewhere. That's the vector. But you can pick a set of unit vectors, I, j, and k. Then the vector will have components vx, vy, and vz. Similarly, psi is a vector without choosing a basis. But if you use the eigenbasis of the x operator and project it on that, that is what psi of x is. Obviously, I have to assume you're familiar with that. I cannot go into that now. So if you want, I can write this more abstractly this way. Use the ket psi without choosing a basis. That's a Schrodinger equation for the ket. Normally, so you can, even in vector analysis, you can draw all the vectors you want with arrows on top of them. But to do any calculation, we resolve the vector in the components, vx, vy, and vz, and we solve for the component. Similarly, psi is usually written in a basis. And if you write it in these in terms of eigenstates of position operator, that projection, which is the component of psi along that state, is psi of x. So this is the complete picture for quantum mechanics. You agree that if you know psi of x, you know what it's good for. You can square it and get the probability. And you can see what's going to happen with time, because the rate of change of psi is given by IH bar d psi dt, the Hamiltonian acting on psi. In the X representation, Hamiltonian acting on psi looks like this. So what you normally do is somebody will give you an initial state or the initial wave function, psi of x and 0, and you have to find psi of x and t by solving the Schrodinger equation. At least mathematically, it's clear what you have to do. In practice, it may not be easy to solve for the evolution exactly, but it has an evolution because once you have the equation of motion, and it's first ordered in time, so if you know psi of 0, you need nothing else. Now I have to ask, how many people have seen this thing called the propagator? Is there anybody who has not seen it? How do you tell? Varun, can you find out how many people know? Have you guys seen the propagator?
Yeah, students can chat use mic. Students can give in chat who has seen. I think sir most of didn't have seen.
They have seen. Okay.
No, they didn't have seen. They didn't have
They have
seen.
not seen. Oh.
Yeah. Okay.
So, well, I will slow down a bit, but you realize no matter how much I slow down, it will still be quite fast. But let me just say, as a mathematical result, that if you take the Schrodinger equation, for every initial state, you can find the final state because of the equation. Now, the answer to that, for every possible initial state, is given by this wonderful formula I've written here. You take the initial state psi, multiply by this u, and integrate over x1, and the function you get is psi of x2 t2. If you want, I can give you an analogy. If you have a vector b, and it's got some components, and there's another vector w, you can write w as an operator times b, and the components will be wi equal to mij bj summed over j. This psi is a vector whose components are psi of x2. This psi is a vector whose components are psi of x1, and this is like a matrix. You multiply over the second index and you sum over the second index, and you get this state. It's like a matrix operation in the world of wave functions. What is surprising, you should think about it. That is actually an explicit formula for this u. So that every problem anybody can come to, you have solved once and for all. You just take the initial state, multiply by u, and integrate over x1. What remains will be a function of x1, x2, x1 and t2. That's the wave function of time t. Now, I will tell you quickly some explanation of how this object arises, but we cannot do that in any detail. How do we find u? Go back to the Schrodinger equation for the Kent psi. Here's the equation. I'm telling you that you can write down by inspection the following solution. I claim the solution of this equation is this. The exponential of the Hamiltonian means, exponential of anything is 1 plus x squared over 2 factorial and so on. You do the same thing with the Hamiltonian. You get an infinite sum over powers of h. That's the definition of exponential. And I claim this is the answer for the initial value problem. Let us check that this is the complete answer for any problem. By the way, this assumes that h does not depend on time. For Hamiltonians that don't depend on time, then you can write a solution once and for all. How do I know this is the right solution? Well, plug it into the Schrodinger equation and see what happens. You take IH bar d psi dt on the left, then you do IH bar d psi dt on the right. Nothing depends on time here. This is the fixed initial state. D by dt acts on this and pulls out the Hamiltonian times this. But this is just a state at time t. You can see that h bar d by dt of psi at time t times psi at time t. Therefore, you can write down an operator. This is what may be news to some of you guys. Give me a Hamiltonian. Think of this operator as an infinite power series in 8, but it's called exponential or Hamiltonian. Plug in the values for initial time and final time. I chose them to be 0 and t. In general, initial time is t1, final time is t2. So e to the IHT becomes e to the IHT t2 minus t1, the general case. That operator, when acting on a ket at time t1, will give you the ket at time t2. That's called the propagator because it propagates the state in future, into the future. Now, we don't want this abstract form. We want it in the coordinate basis. The coordinate basis, you want to project this operator, this matrix elements between the raw x1 and the ket raw x2 and the ket x1. Then you have to do a few manipulations between this one and this one. You want to put a complete set of energy eigenstates, and they're here and here. This one, by definition, is a wave function psi sub n at x2. N is the possible eigenstates of the Hamiltonian. So you can get this. Anyway, I'm going to give these notes to Keshav in PDF. You guys can go and look at it later on and fill in the blanks, or you can read my book or any other book to do this more slowly. But unfortunately, I have to take this result for granted. But what I want you to know is somebody asks you, what is the propagator? You should be able to say the following. In any time-independent Hamiltonian, the propagator is an operator which acts on the initial state to give the final state. It's a function of initial time and final time. And if you write the operator in the coordinate basis, its matrix elements will be labeled by x2 and x1. And here it is. So here is the punchline of the propagator approach. The propagator is given by this. At least that much, all the numbers in this equation you know. So the mysterious thing called propagator is determined if you can give me all the energy eigenfunctions, which I'm labeling by some index n, you can call it En or E, doesn't matter. If you take this product, oh, I made one mistake here, this would be psi star. Then that sum over E or sum over N is the propagator. So you don't know the derivation, but I want to make sure you know what the statement is. I will repeat one more time. In quantum mechanics, there is something called the propagator, which is an operator or a matrix. It acts on the initial state and gives the final state at a later time. It can be fully written down if you give me every single eigenfunction of the Hamiltonian. And it takes this form. Now, we have to do this infinite sum. It's not easy to do infinite sum, but you can write it down. That is once and for all the answer for any initial state. But notice what you need to do that. To write the propagator, you have to take the Hamiltonian and find all its eigenfunctions. Then you got to multiply them. And you must multiply. Yes?
Sir, this propagator is a vector, like there is one index only, and
no, it's a matrix that has got two indices. This is the x2 and x1, or the row and column index, if you like. Use like psi is like a vector. These are the components of psi, and this is like a matrix. Because only a matrix can act on a vector and give you a new vector.
Other student also want to ask. Kritika Andhikari.
Yes.
Yeah, Kritika, please switch on your camera and please ask.
Sir, is it the time evolution operator?
Yes, it is. Yes. Maybe it's called that. I call it propagator because I've seen it somewhere else as a propagator. It's a time evolution operator. The operator acting at initial state you see the state at a later time. This is quite remarkable, by the way. If you go to Newtonian mechanics, there is no such thing. Tell me what you can do to the initial coordinate to find the coordinate at all future times. There's no single thing you can do. You have to solve the differential equation. But here in quantum mechanics, you can write down once and for all some operator that acts on initial state and gives the final state. If you knew the propagator, you know the whole theory because you can predict the future given the present. But to do the prediction, you need to know all the eigenfunctions. So who had that question now? Sorry.
You can continue there, no.
Kritika, you had the question? I forgot who had the question.
Yes, sir, I got it. Thank you.
You got it? Okay, yes, it's the time evolution. So everybody should know, at least like a black box, the fate of the quantum system is fully determined by this operator U. You give me the initial time, and you give me the final time, and you give me all the energy eigenfunctions, and I build this operator, I multiply on the state and integrate it over x1, I give you the state of the later time. That's it. So I'll give you one example of the propagator, or what you call time evolution operator. Take the case where it's a free particle. For the free particle, the eigenstates are labeled by momentum. States of momentum are also states of energy. The energy is just p square root 2m, but p is the momentum. And the wave function is this. So we have the ingredients, the two wave functions you need are just exponentials of ipx over t. The sum over states is replaced by an integral over t. So the propagator, you must do this p integral. This is the psi of x2, psi of x1 star. This is the e to the minus energy times t2 minus t1 over 2mh bar. And this is the sum, which is dp over this. If you do that integral, you will get the propagator for the free particle. Now, this is a Gaussian integral. It's got exponential of the quadratic in p and linear in p, and we know those integrals can be done by completing squares, and this is the answer. So if you don't know that, you can treat that as a black box and say that I know how to do this integral over p, and this is what I get. This is very important. Here's a concrete example of a u. I talked about u of x1, x2, t1, t2. Here is one. Just take a look at it. It's got an x2, the final position, x1 initial position, t2 is final time, t1 initial time. If you multiply this u by psi of x1 and integrate over x1, it will give you psi of x2 at time t2. That's the point. But instead of writing a formal sum, here's a concrete function. So take a minute to look at it, and you should write this down. You should write this down. It's going to be very important. I'll give you a second to grab a piece of paper and write down the propagator for a free particle. Particle with no potential, just drifting at momentum p. Now Feynman is going to give you his rule for quantum mechanics. The wave function is defined as before, but there is no Schrodinger equation in Feynman's language. There is no intermediate wave functions in Feynman's language, but there is a formula for the propagator. So in the standard approach, you get to the propagator in two stages. First, you find all the eigenfunctions, then you multiply them and form this infinite sum, then that's a propagator. But Feynman is going to give you a single shot approach to go directly to the propagator. And we know that once you have the propagator, you can propagate the system in time and you can predict the future. Also, there are other ways to extract from the propagator the wave functions of the energy. In other words, if you give me the energy and the wave function, I can find the propagator. But if you know the propagator, I can also find the energies of the wave function. I won't go into that. Because in Feynman's approach, you don't need any of that. You just want to predict the future. So what is Feynman's rule for the propagator? That's what I'm here to tell you about. That's what the whole lecture today is about. Here's the answer. So So give me a second. I'm going to plug a charger into my laptop. It is threatening to go down any minute. Hold on. Okay, I'm still here. Don't worry. I'm trying to connect a long extension cord. All right, I'm back. Here's the Feynman formula for the propagator. He says, are you guys still there or you lost me? Still there. Okay, here is the rule for propagator for any quantum problem. Any quantum problem. You want it to depend on x2 t2, x1 t1. That's just like in classical mechanics, which are 2 points on a trajectory particle, right? U has the same arguments. To find that, you draw all possible paths connecting these two endpoints. And on each path, you have a number of unit modulus. You know, e to the I theta is the number of unit modulus, but the theta here is S of p over h bar. In other words, for every path, find the action, that namely S of p, take exponential of e to the I s over h bar, and sum over all possible paths connecting these two endpoints. And that is the propagator up to some overall factor in the front. So these are all paths connecting x1, t1 to x2. Anybody have a question about what this is? This is the time to ask, because this is the Feynman recipe. Any question about the recipe?
Sir, I have a
Yep.
question, sir.
Yes.
Sir, this propagator, this is like something we have in quantum mechanics, right?
Yes.
So, sir, the path integral formulation, it
Yes.
talks about the most probable path. It talks about the trajectory. But when we talk about quantum mechanics, we cannot give a trajectory of something, because Heisenberg's uncertainty principle will not allow us to simultaneously give the position and the momentum of
Yes.
something. So how does these two combine to give us this propagator?
Whose question? Varun, are you speaking now? Who is speaking?
Varun, sir, Varun.
Varun, you got very good company, because Mr. Niels Bohr had the same objection to Feynman's formulation when he gave a lecture in the conference. He had the same problem. He said, what are you talking about? What trajectories? Don't you know there are no trajectories in quantum mechanics? Well, that objection, it turns out, is not correct. Feynman is not saying the particle follows a particular trajectory. In fact, the trajectories here are not Newtonian trajectories. They're every possible trajectory connecting these two endpoints. Some of them look like a real trajectory. Some may go to the moon and come back. Some may go to another solar system and come back. You sum over everything. And each path contributes a number of unit modulus, which is the exponential of the action divided by h bar.
Excuse me, sir.
Yep.
But the relativistic thing should be respected here, no? I mean, you cannot include the paths.
No. That's correct. This is not relativistic quantum mechanics. First of all, the paths are not actual paths taken by any particle, so they don't have to respect the limits on the velocity. That's the first thing. Secondly, this is non-relativistic quantum mechanics. So we are solving for the propagator in non-relativistic quantum mechanics. The Feynman's original formula is for non-relativistic quantum mechanics. There's a way to do everything. You go to relativistic theory. I don't think I'll have time to do that. I will tell you how you do it in quantum field theory, which is a relativistic theory, and you will see how it's done. So when you draw these paths, you don't worry about going slower than light, because these are not, look, this is a mathematical gimmick for getting the right answer. Ingredients of the gimmick do not correspond to actual trajectories taken by actual particles. Secondly, you're right. In quantum theory, there is no single trajectory. Particles don't have trajectories. But what's interesting is that quantum theory is described by a sum over all trajectories, classical and non-classical, and anything is given. Every trajectory you can think of is given the same contribution. So what you're supposed to do, imagine you can discretize space and you can count all the paths. You number them, and for each path, you go and compute the integral of kinetic minus potential, you get the action, you take the potential, and that's the number of unit modulus. And for every path, you get that complex number of unit modulus, and you keep on adding them. That sum will give you the propagator. You have to normalize it in the end so that the wave function is normalized, but this is the rule. So the first mystery is, nowhere, look, every path gets a number of unit modulus that looks like this in the complex plane. Unit length at some angle. That angle is just S over H bar. So what you're supposed to do is to, for every path you get an arrow, next path you get another arrow, next path you get another arrow, keep on adding all these arrows, and that sum will give you the answer. Now, the classical path is not distinguished from any of the other paths in Feynman's system. You might think somehow it will get a much bigger share. No, it doesn't. It gets the same unimodular contribution. You can ask, how does classical mechanics emerge when H bar goes to 0? This theory seems to give every path equal weight. And the answer is also contained in this formulation. Remember that if you initially start with some crazy path, it'll have some action. You go to nearby crazy path, it'll also have another action. And each unit vector you get in the complex plane of unit length will be rotating in its space. And if you keep adding all those numbers, they'll be going round and round in circles. Until suddenly, you'll find a whole bunch of paths, all of which have essentially the same action. That means the phase is the same. Those vectors will now add, without cancellation, to produce a very, very long vector going from here to here. Then after that, you're no longer in the region of stationary path, then the action will start changing. So at the two ends, you got stuff that adds up to 0, basically. The main contribution comes from this. So the answer then is that the path integral is equal to some number n times exponential of IS classical over H bar. That's a good approximation of the answer. So this explains how Newtonian mechanics emerges as H bar goes to 0, because here in this formulation, you find classical path and many other paths contributing. But in the real world, particles seem to move on just the classical path and nothing else. The reason is that the phase is measured in units of H bar. If you take an object of mass 1 kilogram and you wait for, say, 1 second to go from here to there, you'll find the classical path is some path. You cannot change the velocity by more than 10 to the minus 17 meters per second. But then the action will change by H bar. Remember, you have action over H bar, so you start at the stationary point, the action is fixed. Once it starts changing by an amount proportional to H bar, you will find the phase begins to randomize, and then you don't get any contribution. So the coherent contribution from paths is in a window where the action cannot change by more than H bar. For a particle of mass 1 kilogram, action is fixed to 1 H bar, means the trajectory is fixed to 10 to the minus 17 meters per second. But if it's an electron moving in an atom, you will find the action can change by H bar without negligible contributions. So the path of an electron in an atom will be very different along this. It does not have a definite trajectory, but once you go to macroscopic objects, only the classical path will matter. So now let us use Feynman's recipe to compute the action for the classical path for a free particle. For a free particle, starts with x1 t1 and goes to x2 t2. The classical trajectory is a straight line at fixed velocity. That's a classical path. In space-time, it's a straight line. The kinetic energy is 1/2 mv squared. The b is just x2 minus x1 over t2 minus t1. So that's t. And it's constant on the path because it's going at constant velocity. So integral of action over time is this multiplied by t2 minus t1. That tells you then this is the propagator, except for a number in front that counts the number of paths for which the action is stationary. And you can determine the number A by demanding that when T1 goes to T2, this should become a delta function. Because at T1 equal T2, the propagator is just a unit matrix. Then you can fix A and you can get entire propagator, which I wrote for you. I told you to write it down. You can now compare what you wrote down to what you get here. So that is the power of the Feynman approach, is that you do one classical trajectory and you take its action and you exponentiate it, that gives a propagator. Remember, this is not the exact answer all the time. It happens to be a very good answer. For the free particle, it is the exact answer. But when does it work? You can show that if the Lagrangian is quadratic, then the coordinates and velocities, like in the harmonic oscillator, this will work. In other words, if you take the harmonic oscillator, you guys have solved it. The answer is a lot of Hermite polynomials. If you take this infinite number of Hermite polynomials, multiply them to get psi times psi star and sum over all the states, you will get a function which will coincide with this exponential here, but that should be the action for a harmonic oscillator going from x1 t1 to x2 t2. But the prefactor A, you cannot find by saying you should go to unit matrix at t1 equal to t2. You have to really do the sum over trajectories near the classical trajectory. How you do the sum and so on, I have not explained. How do you sum over paths is not clear in this elementary treatment. But what should be clear is that we have an answer once and for all, where if you know the classical trajectory, you can go a long way towards the quantum propagator. In general, you won't be this lucky. You will get the exponential part of the answer, but the prefactor is required doing integral. So a brief interlude on quantum field theory, or I should say relativistic quantum field theory. You live in one dimension, that's the field phi of x.
Sir,
Yep.
sir, for one particle, it is perhaps easy to calculate Feynman propagator from Lagrangian. But if there is multi-particle, isn't it will be very much complex?
Yes, that is correct.
It will be complex than perhaps Schrodinger's picture, because there will it will be very tough to solve those integrations. Schrodinger equation. Yeah.
Yes,
How?
you cannot do that. You cannot get all the trajectories of a generic classical problem. So it's just a statement that if you knew that, you can do this. But if you don't know the classical trajectory, every one of them, then you cannot do this one either. But what is remarkable is there is an approach to quantum mechanics based on the Lagrangian, right? Not based on the Hamiltonian. Yeah, that is the contribution that Feynman made. You can work with Lagrangian. I'll tell you why the Lagrangian is the big thing. If you do quantum field theory, and now I'm talking relativistic quantum field theory, the formulation has to be relativistically invariant. But the Hamiltonian in relativity is not a scalar. Hamiltonian is the time component of a momentum energy 4 vector. But the Lagrangian is a scalar. So the exponential of the Lagrangian density here. That is the scalar. So the propagator in the quantum field, if initially the quantum field was in a configuration phi of x1 at time t1. Remember, for the quantum field, x is not a variable. X is a point on the line, and phi is the variable at that point. And you want the whole configuration at one time t1 you want to know what's the probability that it will be in some other configuration at time t2, you must sum over all configurations, starting with the initial configuration, ending in the final configuration. Each one should get a weight which is exponential of I times S over H bar, where action is this for a scalar field. We can see is relativistically invariant. This is all relativistically invariant, and dx dt is Lorentz invariant. So you have now a Lorentz invariant formulation of quantum field theory, which is what people use nowadays. So give me any scalar field or Higgs field or whatever you want, you can do that. You can integrate the Lagrangian and get a Lorentz invariant answer. So I will conclude by saying this objection that came up earlier, they ran into a lot of trouble saying, Mr. Feynman, don't you know there are no trajectories? Another question they had, how about Pauli principle? What if you have two particles, they're running around everywhere and anywhere? What if one of them goes to the same location as another one in your sum over path? Shouldn't that be excluded by the Pauli principle? Well, he had an answer for all of them. But the main answer I'll give you for the first one is, he's not saying there are trajectories. Look, quantum mechanics is a cookbook. It's a recipe for computing things you can measure. The propagator is an essential ingredient in the computation. You can get it using Heisenberg's, or you can use it Schrodinger's equation, or you can get it using Feynman's approach. It doesn't matter. Both of them give the same answer. So the fact that one is a sum over paths is no objection. Finally, you can actually derive the path-critical approach from the standard Hamiltonian approximation. You can see that in my book, or you can see that in any other book. All the objections are not valid. If you got two or more particles, you must do antisymmetry or symmetry, and that'll take care of the particles that try to occupy the same position. They will make zero contribution. Anyway, I want to conclude now because this is really what I wanted to tell you about this formulation. So now you can ask me further questions if you have any.
Students are requested. Sir, you have concluded, sir?
Yes, I'm finished. So I'm waiting for questions. I don't have any more. So, yes.
Okay. Students are now requested to ask questions. Yes, please ask the question.
Sir, I don't exactly have a question, but can you please explain that example of that electron and the classical particle that you have given earlier?
Can someone repeat that a little louder? I didn't hear it.
Sir, the example that you gave about a classical particle and an electron when you were calculating the
Yes.
yes, that example, sir, that I want to understand again.
So here's the picture you have. There are a lot of paths contributing, and only paths with action or within H bar of the classical action will survive. For all the others, the phase is changing very rapidly, and they all add up to zero. So these trajectories I'm showing here, they all contribute, but they don't have the same classical path, but they differ from it by an amount H bar. How wide a difference is that? If you take a macroscopic particle whose mass is 1 kilogram, then you will find out that if it's trying to travel from somewhere to somewhere in 1 second, its velocity cannot deviate from the classical path by more than 10 to the minus 17 meters per second. That means there is no deviation, essentially no deviation. But as the particle gets smaller and smaller, its kinetic and potential energies get smaller and smaller, the action gets smaller and smaller, until when you reach something like an electron, its action within an atom from going from A to B, it's itself of the order of H bar. Therefore, when the path changes dramatically, then you will find they all contribute to the path integral. So the reason classical mechanics no longer works at the quantum level is the trajectory can be modified significantly without changing the action by h bar. For example, I give an example in my book. Take a particle that starts at, I'll give you an example. Suppose you want to go from 0, 0 to 1, 1 for a free particle. The classic trajectory is a straight line, which is x equal to t. Let velocity be 1. There's another trajectory, which is x equal to t squared. Also goes from 0, 0 to 1, 1. You can find the action on the actual path, find the action on the hypothetical path, and you will find if the particle's mass is electron mass, and these are distances like 1 angstrom, the change in the action will be negligible between this one and this one. So in that case, all these paths you can draw will all contribute. And there you cannot say the particle has a trajectory. But if the same problem, if it was an object of mass 1 kilogram, and this is 1 meter apart, and this is the classical trajectory, any other trajectory that's within this window will be no thicker than the pen I've drawn here. So it will seem to go on a classical path. So quantum mechanics is regained for particles whose typical action on a typical trajectory is of the order of h bar. Macroscopic particle action is of order 10 to the 34 h bar, then a change of 1 part in 10 to 34 means a change in the trajectory you will never see.
So now, and so this is the reason like why the classical particles have a very narrow region, so they have a definite trajectory, whereas the quantum particles they have a wider region, so they do not have a definite a trajectory. Whereas classical particles have a very narrow kind of a region where this phase is constructively interfaced. So it's a very narrow region.
Yes, so narrow that you cannot even talk about it. Narrow means 10 to the minus 17. I remind you, the atom itself is like 10 to the minus 10. So you will never see those deviations.
How will compute, sir?
Pardon me?
How will we compute this narrowness? How we will compute?
You can start adding trajectories which differ from the classical path and see when it deviates by more than h bar. Then you will find those trajectories look almost identical to the one that is taken. That's how you will know there are no significant trajectories in this problem.
Okay, sir. Okay.
Okay, any other questions?
Sir. Hello.
Yes, yes.
Hello.
I'm not able to hear you. Sorry.
Since there can be ways of doing classical mechanics other than Newtonian and Hamiltonian English.
There are only three known methods: Newtonian, Hamiltonian, and Lagrangian. I don't know any other ways to do it. And that's one reason you should learn how to do everything in as many possible ways as you can. You never know what will come in useful for some future calculation. The people could have said, well, who cares about Hamilton and Lagrange? Newton's equations tell you everything, but they don't tell you how to go to quantum mechanics.
Sir, okay, sir. Then, sir, we have we have four ways for doing quantum mechanics, right? One is Schrodinger, one is Heisenberg, and other is Feynman approach, right?
Mm-hmm. In fact, Schrodinger and Heisenberg, I would call essentially the same. They're all based on the Hamiltonian. They have the operators. Remember, Feynman doesn't have any operators in his language. And he has trajectories, and they don't have trajectories. So I would think Schrodinger and Heisenberg are just mathematical transformations on whether the operators change the time or the states change the time. So I would say there are two ways to do quantum mechanics: the Heisenberg / Schrodinger approach and the Feynman approach.
Sir, just a trivial question. Sir, historically, if we see, then the Lagrangian approach, Newtonian approach come first, then Lagrangian, then Hamiltonian. Then
Yes.
why Schrodinger started with the Hamiltonian approach? Why didn't start with Lagrangian approach, which historically come first?
That's because Heisenberg, when he tried to derive his quantum mechanics, found the commutator of x and p. So he noticed that he thought of matrices at a time when physicists did not know what a matrix was. That's the brilliance of Heisenberg. He just made up a matrix for the x and a matrix for the p. He found out they don't commute. Obviously, that's going in the operator language with non-commuting things. And from that, Dirac noticed that the commutator is like the Poisson bracket, and he could guess the entire formalism. But there was nothing like Lagrangian that anybody invented at that time. Also, everybody said, look, the whole classical mechanics is bad, the trajectories are bad. Let's not think in terms of trajectories. Here comes Feynman, brings the trajectories back. Everybody thinks it's a step backward in time. But obviously it's not, because he's not saying these paths that you sum over are physical. And you can derive this. You can derive the Feynman formula from the standard operator approach. So it's really as good as the other one. Yeah, as to why Schrodinger did what he did, you can try to read his biography. Those days, there were no real ways to do quantum mechanics. They knew classical mechanics is not working. And I'm not sure what made him write the Schrodinger equation. He tried to do the Hamilton-Jacobi theory and do something. But look, any derivation is a fake because you cannot derive quantum mechanics. What he found was that if you write the Schrodinger equation and you find the eigenfunctions for hydrogen, they coincide with the experimental data. That's the only way to know that Schrodinger is on the right track. To me, it's remarkable that from the data, you can extract this formalism of quantum mechanics. Look, it's hard enough to learn it, right? How do you discover it from atomic spectra? I think that's very remarkable. Unlike Newtonian mechanics, where you can see the objects you're studying, in quantum mechanics, you cannot see anything. All they do is emit light, and you have the spectrum. From that fingerprint, you have to deduce the whole formalism.
But that didn't come also by one day. First Niels Bohr gave, and then they tried to develop more things.
Yeah, I mean, quantum mechanics has many parents. I mean, there are many people, unlike relativity, which had essentially one parent who gave the theory in its final form. Quantum mechanics was discovered by many people in many forms. So you would think it was all over. When Feynman came along, it was pretty much settled. But then he brought this new way, and surprisingly, it's very, very useful to think in his language.
Sir, is there a way in which we can tell that Feynman approach and the other Dirac, like Schrodinger Heisenberg approach, are equivalent?
Yes, you can. You can find it anywhere. If you look at my quantum book, there's a derivation of the path integral approach from the Schrodinger approach. Yes, you can do that.
Okay, sir. Okay.
Hello, sir.
Yes.
Sir, what are the applications of using Feynman recipe over Schrodinger recipe?
Yes. I mean, where do you use it? Is that your question?
Yes, sir. I think it becomes quite messy calculation.
Look, there is no simple way to do quantum field theory. What happens in Feynman approach is that in the end, you can never do the path integral exactly, but you can get the answer to your question in a power series called perturbation theory. So perturbation theory is what you use the path integral to do. If the action is quadratic in the field and the derivatives, you can get the exact answer. If it's not quadratic, if it like the scalar field has 5/4 in it, then you do a power series and you expand the answer in powers of some coupling constant. And the advantage of the Feynman approach is that you can do the expansion in terms of Feynman diagrams, and it's completely relativistically invariant. Long before that, people used to do old-fashioned perturbation theory, which is not relativistically invariant. and you do it in one particular frame, and you spend a lot of time proving the answer did not depend on the frame you picked. Feynman's answers is already Lorentz invariant. So the real way people do field theory is by perturbation theory. So Feynman did his perturbation theory, and he made up those diagrams. And those diagrams I've not talked about. That's how people do field theory in practice. But it's satisfying to know that for any field theory, no matter how complicated, you can write down a formal expression for its propagator. You cannot evaluate it, but you can write it down.
Okay, sir.
Okay, I have time for just one or two more questions. At 10:25, I have to go somewhere else. So, anything else? I think what you should do is, I'm going to post these notes, even though they are very hard to read. It's better than not having them. I'll send a PDF to Keshav. He can share it with you. And you should read all the other books in which this problem is treated. This is just to tell you there is another way to do quantum mechanics. Also introduce you to the notion of the propagator or the time evolution operator.
So just last question, sir. Like in Feynman approach, when you were explaining the equation, you tell that it is relativistically invariant. Sir, how from just looking you context, like we have to solve for that? How?
Your sound is breaking up. Yeah, Keshav, you have to say that again.
Sir, when you can you hear me now? Good. Okay.
Yes.
Sir, when you were explaining, sir, in one equation, like above in the PDF, you say that that approach was relativistically invariant, sir.
Yes. Yes.
Sir, how can you how we from just observing we can say, sir?
Oh, because you look at what you do here, you are summing over configuration. The action is got a Lagrangian density integrated over space and time. That dx dt is Lorentz invariant. If you go to a different frame of reference where x and t undergo Lorentz transformation, you can show dx dt remains dx dt. But dx dt is the volume of space-time, and that's a Lorentz invariant. You have to actually prove that. Then this thing you're integrating here is also Lorentz invariant, because this phi dot squared minus grad phi squared is Lorentz invariant. That means if we go to another frame of reference with a new time t prime, a new coordinate x prime, it'll have exactly the same form and exactly the same numerical value. And phi is a scalar field. That means its value is the same in all frames. V of phi is also Lorentz invariant. So you can show there is a Lorentz transformation of the coordinates and time, x and t, that leaves this action invariant. If you're summing an invariant over different configuration, the answer is also going to be invariant. That's a very powerful thing. You cannot do this with Hamiltonian. You cannot prove the theory is Lorentz invariant, because you must write a Hamiltonian. For that, you must pick a frame of reference. You can compute everything you want, but how do you know your theory will be the same in a different frame? You have to prove it each time. Good example is electromagnetism. For electromagnetism, the Lagrangian density you have here is really E squared minus V squared. But E and V are electric and magnetic fields. That is the Lagrangian density for electromagnetic field. And E squared minus B squared happens to be Lorentz invariant. So this is how you do electromagnetism in a relativistically invariant way.
Okay, sir. Nice to see the work of the Feynman. Sir, one last question, perhaps different from this. Sir, is the Feynman has also work in field theory, like the work of renormalization. Is that completely different from this path integral?
No, he used the path
How?
integral to get the power series for the measured quantities. For example, one quantity everybody was trying to compute just after the war was called G minus 2. The magnetic moment of the electron was supposed to be 2 in some units in the Dirac equation. An experiment showed that it's slightly different from 2. And that turns out to be due to the fluctuations of the quantum field, and everyone was trying to compute that G minus 2. So Feynman uses diagrams to compute G minus 2. And then after a while, everybody started using the diagram because it's a nice way to organize perturbation theory. So I'm sorry, what was your question now?
I was asking that Feynman has also done work in quantum field theory in the renormalization. How was related?
Yes, right. So if you do the perturbation theory, you can expand, suppose phi, B of phi here. Suppose B of phi has got a phi squared term and a phi fourth term. You can only do perturbation theory in powers of lambda. And if you start doing perturbation theory, you'll find you can write the terms in terms of diagrams. And by the way, the diagram involves what I just call the propagator. Those lines you see in Feynman diagrams are the propagators connecting those 2 points. But you find that the answer is infinite the minute you do more complicated diagrams, and you need a way to subtract from that infinity some number to get a finite answer. If you subtract too much or too little, it doesn't work. How do you subtract the right amount? Well, for that, Feynman's approach gives the best way, because you must make sure that what you're subtracting is a Lorentz invariant quantity, so the answer doesn't depend on who's doing it. So he found a way to deal with infinities, and so did Schwinger. That is one of the main contributions, is how to extract the finite part of infinite answers in perturbation theory. So he did that, then he and Gell-Mann tried to do B minus A theory. But B minus A theory had been written down in some form by Marshak and Sudarshan. They didn't pursue it too far, but these guys went further and got some numbers. That's one of the things Feynman feels he did that was not simply redoing what other people had done. He underestimated the path integral as simply doing what others had done. But I think it's not fair, because that is a way of thinking that's now dominating the way people do quantum field theory. He also showed how to use his path integral approach to do problems like the superfluids.
Nice to hear how will this path integral approach will coming in the subject. We will learn this more. Thank you.
Okay, so I'm going to say goodbye to all of you. Thanks for being there.
Thank you, sir.
I enjoyed it very much. So bye-bye. I'll send the notes to Keshav.